Hi, this is Dr. Collins Jones again, and this is segment 4 of my quick review of solution and dilution lab math video series. In this segment, we're going to learn how to calculate the amount of each component required to prepare a multi-component solution at specific concentrations. There are 3 worked out examples in this particular segment. They are a little bit redundant, but I've changed things up in order to try to help you pay attention to the different units that you may encounter as you solve these kinds of problems, whether it's on an exam or whether it's looking at a recipe that you may have obtained to make a particular solution from the web or from a lab manual or something like that. So let's get started. Example 1. Calculate the amount of each component required to prepare 1.75 liters of a solution that is 55.0 millimolar heaps, 1.500 molar sucrose, 10.0 molar EDTA, which is supplied as a 0.500 molar EDTA stock solution, and 0.0075 milligrams per mil of lupeptin, and then finally describe the preparation of this solution. So before we get started, I always like my students to know what each component does or why it's in a particular solution. So let's just quickly go through each of these components and explain their purpose. Heaps, if you recall from previous segments, is a buffer, and buffers resist changes in pH. So if a small amount of acid or base is added into a buffer, the buffer essentially absorbs it, neutralizes it, prevents it from changing the pH. The sucrose increases the osmolarity, and it increases, in this case, at this high concentration, probably increases the viscosity of the solution. With a higher osmolarity, we may help to prevent subcellular organelles from bursting due to changes in the osmotic pressure. But more importantly, if we increase the viscosity, that may decrease the amount of protein denaturation. EDTA is a chemical that binds or chelates, and chelate is spelled CHELATE. EDTA binds or chelates divalent metal cations. And remember that a divalent metal cation is a cation that has a +2 charge. So this would be things like magnesium, calcium, lead, that is lead in the +2 oxidation state, copper +2. But normally we think of EDTA as binding calcium and magnesium, but it can bind other divalent metal cations. And when EDTA binds divalent metal cations, it limits the access of those metal cations to enzymes which may require, for example, calcium or magnesium for their activity. And the other thing is by removing divalent metal cations from solution, it can help to prevent or minimize protein aggregation by preventing the formation of these metal ion bridges between 2 different protein molecules. So EDTA has multiple purposes in a buffer solution, and then lupeptin inhibits proteases. So lupeptin inhibits proteases, and recall proteases are enzymes that hydrolyze peptide bonds, resulting in the degradation or breakdown of other proteins in the cell. So putting all that information together, this is a buffer that is probably designed in the initial step of homogenization of cells or tissues, that is, breaking the cells open to release the proteins, which could then be used as a crude homogenate for protein assays, or could be subjected to a protein purification process. So let's get started then with how to do the calculations to determine how much of each component we need to add in to the 1.75 liters to get to the desired concentrations. If you recall in one of the early segments when I gave you a sort of a step-by-step roadmap about how to do these calculations, one of the first things we said was treat each component separately, as if it's all by itself in the solution, and then we can combine everything after all of the calculations have been completed. So when I do this, I just do it right in order, in the order that they appear in the recipe or in the exam question. So let's start with heaps. Okay. Heaps we see is 55 millimolar, and we're preparing 1.75 liters of 55 millimolar heaps. So we have a molarity and a volume, so we're going to need to determine the number of grams. So we're going to use the formula molarity times liters times molecular weight equals the number of grams. So we need to identify a numerical value for each of these variables in the equation. So we'll start with molarity. The molarity of heaps is given as 55.0 millimolar, but when we solve molarity problems, the concentration needs to be in units of molarity. So we're just going to do a quick conversion here. 55 millimolar times 1 molar per 1,000 millimolar gives us 0.0550 molar, right? The volume, when we calculate the number of grams from a molarity value, has to be in liters, and in this problem the volume was in fact provided in units of liters, so no conversion is necessary. It already was given to us in the correct units. And then the molecular weight, we can look up the molecular weight on the internet. Just search what is the molecular weight of heaps, and the molecular weight of heaps is 238.31 grams per mole. So we have all of the values required. We're just going to plug them in where they belong in the initial equation, and so we have grams is equal to 0.0550 molar times 1.75 liters times 238.31 grams per mole. When you do this on your calculator, at least mine gave 22.937338 grams. That's a lot of digits. And if you look up in the original problem, we see that there's 3 significant figures in the volume, and there's 3 significant figures for the molarity of heaps. So our answer has to have 3 significant figures. So when we do the roundup, we see that we get 22.9 grams of heaps. So we've solved how much heaps we need. What's the next component? It looks like it's sucrose. And so sucrose is given to us as a molarity again, and we have a volume. So given that we have the molarity and volume for sucrose, we're going to use the same equation. Molarity times liters times molecular weight. But here, the molarity is actually provided as 1.500 molar, so there are no conversions needed. The volume in liters, again, is given to us as 1.75 liters, so no conversion. And we can look up the molecular weight of sucrose on the internet, and that turns out to be 342.2965 grams per mole. Again, we just plug the numerical values into the equation, do the math on your calculator, and we need 898.527 grams. But once again, we have too many digits in order to comply with our need for significant figures. And so when we round this up, it's going to be 899 grams of sucrose, because while the molarity of sucrose is 4 significant figures, the volume is 3 significant figures. Okay, so now we've got 2 of these components calculated. What's the next one? The next one is EDTA. Okay, it's EDTA. But here we see that EDTA, the information for EDTA, we are given 2 concentrations, 10 millimolar EDTA and 0.500 molar EDTA, and a volume. So this is our favorite equation, C1V1 equals C2V2. So again, we need to identify the numerical value for each of these variables. So C1, again, is the larger concentration. So C1 is going to be 0.500 molar, because we know that millimolar makes this a much smaller number. All right, so we have 0.500 molar for the initial concentration. If we convert the millimolar value to molarity, right, shown here, then our final concentration is 0.0100 molar. So just double checking, confirming that this number is smaller than this number. And then it said to prepare 1.75 liters. And I have converted the 1.75 liters into milliliters because I know that the EDTA is provided as a solution. So we're going to be measuring a volume, and our volumetric measuring devices in the lab are calibrated in milliliters. So we might as well do the conversion right up front. So we've identified each numerical value. We're going to plug those into the equation, and we get 0.500 molar times the initial volume is equal to 0.0100 molar, the final volume, times 1,750 mils, the final volume. So we solve for V1, divide both sides of the equation by 0.500 molar, and that gives us an answer of 35.0 milliliters of 0.500 molar EDTA. And so if we look at this answer, first let's just check, do we have the right number of significant figures? It looks like we do. 3 significant figures. There's 3 for the 10.0 millimolar, 3 for the 0.500 millimolar, and 3 for the 1.75 liters. So as you go through these problems, we want to think a little bit more practically. How would you deliver this, right? So how would we measure out 35.0 milliliters of 0.500 molar EDTA? In our labs, we would either use a 50 ml serological pipette or a 50 ml graduated cylinder, and we would specify whether to use the pipette or the graduated cylinder in the SOP used to prepare this buffer. So we finished EDTA. What's next? Last on the list is lupeptin. Okay? And lupeptin is given to us as a mass per volume, milligrams per mil problem, right? So this is a simple mass to volume ratio, and we're going to need to calculate this in grams because, again, our balances are calibrated in grams, not milligrams. Some balances do have a display feature where you can actually display the weighed value in milligrams, but ours do not do that. So we need to have all of our final calculations in grams. So this is a fairly straightforward problem. If you recall from segment 2, grams will be equal to the volume to prepare in milliliters times milligrams per 1 mil, since our unit is per mil of lupeptin. So we just plug those values in. Again, we've converted the liters into milliliters. You've seen that over here. So it's 1,750 mils times 0.0075 milligrams per 1 mil. That gives us 13.125 milligrams, right? But we're going to convert that into grams. So it's 1 gram per 1,000 milligrams. That's our conversion factor. And we note that there's only 2 significant figures in our concentration of lupeptin and 3 for the volume. So our answer must only have 2 significant figures. Okay. And then the last part of this problem is to describe the preparation of this buffer. Right? Now, this is a generic description, and I asked my students to do this on the quizzes or exams because I just want them to have the general flow of how things work. But we prepare all of our solutions in the lab by SOPs, and the SOPs provide a little bit more detail. They have data tables, they have traceability tables, and things like that. But this is just sort of a quick overview to always remind people what we do when we prepare a solution. So the first thing we do is record traceability and complete the data forms in the SOP or batch record according to Alcoa Plus directions. Okay. Then we measure the calculated amount of each component. We weigh it out, we measure it out with a volumetric measuring device, but we weigh each component, and we dissolve all of those components in approximately 2/3 of the final volume of the solution that we want to prepare, right? All in the same vessel, right? So all 4 of those go in to roughly 1.1 liters. We completely dissolve that. once all the components have been dissolved, we then QS to the final volume. And QS means you just add enough of the solvent to this, in this case, ultra pure water, to bring the final volume to our desired 1.75 liters. Then we label the container that the buffer is now prepared in, and we store it appropriately. Do we need to refrigerate it? Do we need to put it in the dark? Can it be at room temperature, whatever? And all of that should be indicated as part of the label. And again, we have a specific SOP that tells you how to write a label for solutions that are prepared in-house in our lab. And of course, the whole time we are following the quality principle of 6SE, right, where the main components here are follow all the safety requirements, proper PPE, proper waste disposal, okay, and making sure that we clean up the area and put everything back where it's supposed to be. So this would be the answer that I would expect for any solution that you're going to prepare. The only thing that will change are the solution components, but everything else would be exactly the same when I ask a student to describe how to prepare a specific solution. So that's the end of example 1. Let's move to example 2, where basically it's going to be the same set of equations, but I've just changed the units up a little bit so that you can get some practice dealing with different units. So in this example, we're asking you to calculate the amount of each component required to prepare 250 mils of a solution that is 150 millimolar MOPS, 0.500 molar KCl, 15 millimolar EDTA, 0.025% volume Triton X100, and that tells us that Triton X is supplied as a liquid since it's volume, and 6.75 milligrams per mil gamma globulin. And again, just for the practice, describe the preparation of this solution, okay? Quickly going through the components, MOPS is another chemically synthesized buffer, okay? So it's more stable, especially when it comes in contact with enzymes. KCl, potassium chloride, as you know, is a salt. This sometimes helps to solubilize and stabilize proteins in solution. It also helps for peripheral proteins, those that are associated on the surface of the membrane, to break free from the membrane surface. EDTA, you guys are experts in EDTA, right? EDTA chelates divalent metal cations like calcium and magnesium. Triton X100 is a non-ionic detergent. It is often used to solubilize membrane proteins. It helps pull proteins out of the cell membrane, and it also can help to solubilize other hydrophobic or non-polar molecules in the solution. And then gamma globulin is a protein that we add sometimes to help stabilize other proteins or prevent non-specific absorption of cellular proteins to the surface of the glass or plastic that our protein solution is going to be in. Let's get started on the calculations. So again, we're going to do this, treat each component individually, and we'll start with MOPS because that's first up in the problem. So MOPS again is supplied, the information for MOPS is given to us as a volume and as a molarity. All right, so it's given to us as a volume and a molarity. So hopefully you thought, okay, we're going to use to calculate the number of grams of MOPS that we need. It's going to be molarity times liters times the molecular weight. So here we have the molarity is given to us in millimolar again. So we need to convert millimolar into molarity. And when we do that, it's 150 millimolar times 1 molar per 1,000 millimolar, or 0.1500 molar. The volume in this problem is given to us in milliliters. And whenever we're calculating, our calculation involves molarity, we need to convert milliliters into liters. And so that's just 250 milliliters times 1 liter per 1,000 milliliters. Okay. And as before, for any compound, we can always look up the molecular weight on the internet, or oftentimes it's printed on the label of the reagent bottle. And so the molecular weight of MOPS is 209.26 grams per mole. So again, we have a numerical value for each variable in the equation. So we're just going to plug these in. Grams is equal to 0.1500 molar times 0.2500 liters times 209.26 grams per mole. This gives us an initial answer of 7.84725 grams. But by now I know you're thinking this is too many digits. We're not obeying the rules of significant figures. So we look up and say we have 4 significant figures for MOPS, 4 significant figures for the volume. So our answer should have 4 significant figures. And there it is, right? Accounting for roundup as well. All right, what's next? Looks like it's KCl. So here we have, again, for KCl, a volume and a molarity, right? We have a volume and a molarity, so we're going to need to determine the number of grams of KCl. Same formula as before, grams is equal to molarity times liters times molecular weight. So again, we need to identify the numerical value for each component and see if we need to do any conversions to get them into the proper units. So if we look at molarity, in this case, the concentration of KCl is given to us directly as 0.500 molar, so we do not need to do any conversion here. We still have the same volume, so we're going to need to convert the milliliters into liters, right? And then again, we can use the internet to look up the molecular weight of potassium chloride of KCl. So again, we have all the numerical values. Let's plug these into the equation, right? And then run that through your calculator. And we get 9.31891 grams. And I know for sure now that you're thinking, wait, that's too many significant figures. So we're going to look up here and we're going to say we have 250.0 mils of solution. That's 4 significant figures. And we have 0.500 molar KCl. That's 3 significant figures. So our answer should have 3 significant figures. And we have to do the roundup because the next digit after the 1 is an 8. And so we end up with 9.32 grams of KCl. All right. What's next? Next is EDTA. And so EDTA is supplied to us as a stock solution. So we're going to have 2 concentrations and a volume, making this yet another C1V1 equals C2V2 problem. So again, we need to identify each component and account for any units. All right. So C1 is 0.250 molar EDTA. C2 was given to us as 15 millimolar, right? So we needed to convert that to 0.150 molar. And the volume is given to us in mils. And we know that, especially since it's only 250 mils of solution we're preparing, we're going to leave this as milliliters. We don't need to convert. So solving for the initial volume V1, divide both sides by 0.250 molar, and we get 15.0 milliliters of EDTA. And look, we have 4 significant figures for the volume, 3 for the stock solution, and 3 for the working solution, that is the concentration we want to prepare. So our answer should have 3 significant figures. 15.0 mils of 0.250 molar EDTA, right? Put in a final volume of 250 mils. What's next? Triton X100, our detergent, okay? So Triton X100 is given to us as a percent volume. So because it's volume, we know it's a liquid, and we're going to use this as a C1V1 problem. We could have used this as the mils to prepare times the percent over 100, but I wanted to introduce here a new concept, and that is if we are given a liquid, right, and there is no second concentration, then oftentimes, unless alternate information is provided, unless a different value is provided, if we only have one value for the liquid, and we're told it's a pure liquid, then we assume that the concentration is 100%. And so we can turn this into a C1V1 equals C2V2 problem, right? Because the concentration of a pure liquid is 100%. All right, so C1 is 100%, C2 is 0.025%. We're trying to calculate the initial volume, that is the volume of pure Triton 100X that we need to deliver into a final volume of 250 mils. And the final concentration is 0.025%. So we have all the variables. We're going to plug them into our equation. And it looks like this. 100% times V1 is equal to 0.025% times 250. Solve for V1. So we divide both sides by 100. And this gives us 0.0625 mils of Triton X100. So this is less than a mil of Triton X100 that we need to deliver. So that means that we're actually going to need to use a micropipette men, right? And those are calibrated in microliters. So we're going to need to convert our 0.0625 mils into microliters, right? Or 63 microliters of Triton X100. One additional sort of practical fact that I want to point out here is that a lot of these liquid detergents, especially the non-ionic ones, are very viscous, right? They're thick. They're like honey. So they are very difficult to pipette, whether it's a micropipette or serological pipette. They are very difficult to pipette. And so oftentimes we have to use a specialized pipette in order to pipette pure Triton X100, pure Tween 20, pure Lubral, called a positive displacement pipette. All right, and that accounts for the viscosity. Alternatively, sometimes researchers will take the pure Triton X100 and dilute it to, say, 50%, and that decreases the viscosity, the thickness of the solution, that we are able to accurately pipette it with a normal micropipette. But just sort of an aside there to think about when you're dealing with these really viscous, really thick solutions. Okay, so we've done Triton X100, right? And again, 3 significant figures because we only have, 2 significant figures. Whoops. We have 2 significant figures because our given concentration is 2 significant figures. So what's next here? Finally, we end up with gamma globulin. And again, gamma globulin is given to us as a mass per volume. Okay, the gamma globulin is given to us as a mass per volume. So we're simply going to use grams is equal to the volume to prepare in milliliters times milligrams per mil, because again, the unit is milligrams per mil. So we just plug this in, 250 mils times 6.75 milligrams per 1 mil gives us 1,687.5 milligrams. But you guessed it, our balances are not calibrated in milligrams, so we need to convert this to grams. And if we take into account significant figures, 3 for the concentration of gamma globulin, 4 for the volume, so our final answer has to have 3 significant figures. Okay? And then very briefly describe the preparation. It's essentially the same thing because we just want people to keep in mind the steps when you prepare this, not write out the full SOP. So again, record the traceability and complete the data forms in the SOP or batch record according to Alcoa Plus requirements. Measure the calculated amount of each component. Dissolve all of those components in approximately 2/3 the final volume. Once everything is dissolved, then bring this to the final volume, label, store, and follow 6SE. Now, one challenge with this sometimes that people do is if you have a detergent, Triton X100, Tween, Lubral, SDS, Chaps, you don't add the detergent till you have QS'd. Because once you add the detergent in and you're stirring, oftentimes the detergent makes bubbles and it becomes impossible to bring this up to the correct volume. And again, those sorts of differences will be stipulated, specified in the SOP. And that's the end of example 2. the last example, if you've made it this far, the last example, example 3, is calculate the amount of each component required to prepare 82.5 mils of a solution that is 1 molar KCl, 1.5% weight volume NaCl, 2.0% volume Lubrizol, 8.5 millimolar dithiothriotol, and 0.5 grams per liter BSA. So most of these components, you already know what they are, right? The salts help in solubilization. Lubrizol is a detergent, which is just a different detergent to extract membrane proteins and stabilize them. Dithiothriotol is new. Dithiothriotol prevents the breakage of disulfide bonds, so it prevents the reduction of a disulfide bond and SS bond being broken to and two SH bonds. So this preserves that part of protein structure which is required when we have a disulfide bond. So that's dithiothriotol. It doesn't smell very good, so a lot of times people use dithiothriotol in the chemical fume hood. Dithiothriotol comes as a solid powder. And then BSA, very similar to gamma globulin, but BSA is much cheaper, much more abundant. But again, BSA is often used to help prevent the surface denaturation of proteins and to prevent nonspecific absorption of proteins to the plastic or glass surface that our protein solution is in. So if the BSA or the gamma globulin is in the glass solution before our protein solution is in there, it covers all the sites that our protein of interest may adsorb to. All right, so let's get started here. What do we have first? We have KCl. All right, so KCl, we're given a volume and a molarity. I'm not putting the arrows in because I'm hoping you will be able to pick these out as you work through the problem. Okay, so grams, we're calculating the grams of KCl. It's the molarity times the volume times the molecular weight, right? Same as before. So the molarity is given as 1.00 molar, so it is already a molar solution. No conversion is necessary. But we are given the volume in milliliters, and whenever we are dealing with molarity, the volume must be in liters. So we're going to convert 82.5 mils to liters, right? And again, for KCl, we once again look up the molecular weight, 74.5513 grams per mole. So we have all the numerical values. Let's plug those into the equation. 1.00 molar times 0.0825 liters times 74.5513 grams per mole. We get our answer of 6.15048 grams. But you know, too many significant figures. So we look up here. 1.00 is 3 significant figures. 82.5 is 3 significant figures. There's 6 significant figures here. So our final answer has to have 2 significant figures. Okay, what's next? NaCl. All right, so NaCl, right, in this case, is given to us as a percentage, a weight volume. So we need to determine the grams given the weight volume. So this becomes a grams is equal to the volume to prepare in milliliters times the grams, that is the percentage, per 100 mils, because now we have a percentage and the 100 mils goes into the denominator. Since this is a percentage, we are calculating a concentration with units of percent, there is no need to know the molecular weight of NaCl. Whenever dealing with percents, there is no need to know the molecular weight to solve the percentage problem. So we just plug the numbers in, 82.5 mils times 1.5 grams, that's our percentage per 100 mils. That equals 1.2375 grams. If we round this up, because there's only 2 significant figures here, this becomes 1.2 grams of NaCl. All right, next, what do we see here? Lubrizol, which is a detergent. And again, we see the concentration is 2.0% volume. So we know that Lubrizol is a liquid. All right, so we need to determine the volume percent. And here, unlike what we did with the Triton X100, we're just going to do volume to prepare in mils times mils as a percent per 100 mils. But we could also assume that Lubrizol is a pure liquid, and so its initial concentration is 100%, and solve this as a C1V1 equals C2V2 problem. But I thought I'd use this example to show you the alternative way to solve this. So it's just 82.5 mils times 2.0 mils per 100 mils. That's our 2.0%, right? We get 1.65 mils, but again, we can only have two significant figures in our final answer. Since the next digit is a 5, we round up, and so we have 1.7 mils of Lubrizol with two significant figures. All right, next, dithiothiazole, right? Again, prevents disulfide bonds from being reduced, maintains the tertiary structure of a protein. Dithiothiazole, as I mentioned in the initial reading of the problem, is supplied as a solid, right? And so we're given a millimolar concentration to calculate. So grams is going to equal molarity times volume times molecular weight. So we need to convert the 8.5 millimolar into a molarity, and after we do that conversion, we see that we have 0.0085 molar dithiothiazole to prepare. We need to convert the volume into liters, and so 82.5 mils becomes 0.0825 liters, and we can look up the molecular weight of dithiothiazole, which is 154.25. So again, we have all the numerical values. We're going to plug those into the equation, run it through our calculator, and come up with an answer of 0.1081678 grams. You guessed it, too many significant figures. All right, so if we look at this, the dithiothiazole, we only have two significant figures here, 8.25. So our answer can only have two significant figures. The next digit over is an 8, so we're going to round this up. So we need to weigh out 0.11 grams of dithiothiazole. Okay, what's next? Last but not least is our BSA. And the BSA is given to us as grams per liter. So this is a little bit different mass per volume, and that's why I included this. But again, we're still going to use the same equation. Grams is equal to volume to prepare times the grams per liter. All right, and in this case, right, the volume to prepare is in liters, so our denominator must also be in liters. And I apologize, the percent should not be here. It's just grams per liter. But I've recorded too long to go back and re-record this. All right, so this percentage right here is wrong. Sorry about that. So notice the unit grams per liter. So we're going to need to convert our 82.5 mils to liters because we want our final value in liters. And so again, as before, this is 0.0825 liters. But notice all the way through, even though I've done the same conversion over and over again, I'm just making sure that I follow the pattern so that it sticks in my mind about how to solve these problems. So now we have the volume that we need. We're going to plug it into the equation, and this is 0.04125 grams of BSA. Right? If we look at this 0.0500 grams per liter is three significant figures. There's three significant figures in the volume, so our final answer must have three significant figures. And then what's left, describe the preparation, and you should now be able to do this. Record traceability data and complete the data forms to comply with Alcoa Plus as you write in the batch record or the SOP. Measure the calculated amount of each component. Dissolve all those components in 2/3 of the final volume. Once everything is dissolved, QS to the final volume, right? Then label this solution and store it appropriately, right? With dithiothiazole, you probably want to keep it cold, +4 degrees. Don't freeze any solution once you prepared it, because freezing may cause some of the solute molecules to drop out of solution, and sometimes they don't redissolve. But dithiothiazole is known to be light sensitive, and it will degrade at room temperature. So you want to put this in +4 degrees in the dark. And then, of course, follow 6SE, follow all the proper safety requirements, wear proper PPE, work in the proper environment with dithioetheriol. That would probably be the chemical fume hood. Clean up and put away everything after you're done. And that's the end of example 3 and the end of segment 4. One more segment is coming up, and that will be segment 5, which deals with dilutions and serial dilutions.